We have here a theoretical and BOD problem. So, first question nato. So, natin do ka question, first question, second question. So, let's start and deal with the first question. Compute the theoretical and BOD of wastewater containing 30 mg per liter of ammonia as nitrogen. So, knowing na mo na siya itong overall reaction for ammonia oxidation and for this reaction, the theoretical NBOD can be calculated as follows. So NBOD is equal to gram of oxygen used over the gram of nitrogen oxidized is equal to 4 times 16 over 14, which is equal to 4.57 oxygen per gram of nitrogen. Yan, ito. So, to get the theoretical NBOD, so, ato lang buhaton is, i-times lang nato, i-multiply lang nato ni, 30 mg of nitrogen per liter sa kani. So, 4.57 mg of oxygen per milligram of nitrogen. So, kung multiply nato na silang duha, ang magawas ani is 137 mg of oxygen per liter. So, mani siya. Muna na atong answer sa first question, which is kani. So, a theoretical NBOD of the wastewater containing 30 mg of liter of ammonia as nitrogen, ang theoretical NBOD niya is 137 mg of oxygen per liter. For our second question, if the wastewater analysis was reported as 30 mg per liter of ammonia, what would be the theoretical NBOD be? So, first step nato diri to answer the second question, we must convert the mg per liter, kani mg per liter siya, mg per liter of ammonia to the ammonia nitrogen by multiplying the ratio of the gram molecular weight of nitrogen to ammonia. So, to do that, i-multiply na nato no. So, 30 mg of ammonia per liter times 14 grams of nitrogen divided by 17 gram of ammonia. So, ato lang siya i-divide na din, i-multiply ani. So, mano siya ang mugawas niya. 24.7 mg of nitrogen per liter. So, since na naman nanatay converted, so para makuha na nato ang answer ang theoretical and BOD, i-multiply lang nato the same as what we did diri i-multiply lang nato ni kanisya with this. So, let's do that na. The theoretical and BOD is equal to kani butang nato 24.7 milligrams of nitrogen per liter. I-multiply nato ani. Okay? So, 4.57 milligram of oxygen over per milligram of nitrogen. So, ano siya? So, i-multiply lang nato ni siya, 24.7 times 4.57. So, the answer will be 113 milligram of oxygen per liter. So, muna siya ang ato ang theoretical and BOD sa kaning second question nato. So, muna ato ang theoretical and BOD problem.
Strathophilps DO-SAG curve. One of the major tools of water quality management in rivers is the ability to assess the capability of streams and to absorb the waste load. This is done by determining the profile of DO concentration downstream from a waste discharge. This profile is called the DO-SAG curve because the DO concentration dips as oxygen-demanding material are oxidized and then rises again farther downstream as the oxygen is replenished from the atmosphere. To develop a mathematical expression for the DO-SAG curve, the source of oxygen and the factor affecting oxygen depletion must be identified and quantified. So we have here the sources of oxygen. The only significant source of oxygen are aeration from the atmosphere and photosynthesis in the aquatic plants. The factors affecting the oxygen depletion. So we have a large range of factors. So we're gonna chop it. So let's start with the most important. BOD, carbonaceous, nitrogenous, and the BOD already in the river upstreams of the waste discharge. Second most important, DO in the waste charge is usually less than in the river. while other factors, non-point source pollution, respiration of organisms living in the sediments, and the respiration of aquatic plants. Number one, mass balance approach. Simplified mass balance help us understand and solve the DO-SAG problem. Three consecutive, those without chemical reaction, mass balances may be used to account for initial mixing of waste streams and rivers. DO, carbonaceous, BOD, and temperature all changes as a result of mixing of the water streams and the rivers. Once this accounted for, the DO-SAG curve may be reviewed as non-consecutive mass balance, that is, one with reaction.
Conservative mass balance diagram for DO mixing. So we have on our left is the mass of DO in river. On the top is the mass of DO in wastewater, and going out is the mass of DO in river after mixing. The product of the water flow and the DO concentration yields a mass of oxygen per unit of time. Mass of DO in wastewater is equal to QW times DOW, and the mass of DO in river is equal to the QR times DOR, where QW is the volumetric flow rate of the wastewater, QR is the volumetric flow rate in the river, and DOW is the dissolved oxygen concentration in the wastewater. Now we have the mass of DO in river after mixing equals the sum of the mass flow. In similar fashion for ultimate BOD, mass of BOD after mixing is equal to QW times LW plus QR times LR, where LW is the ultimate BOD of wastewater and LR is the ultimate BOD of the river. The concentration of DO and BOD after mixing are the respective masses per unit time divided by the total flow rate, that is the sum of the wastewater and the river flows. So DO is equal to QW times DOW plus QR times DOR over the QW plus QR. And LA is equal to QW times LW plus QR times LR over QW plus QR. Now we have here a problem. The town of the State College discharged 7,360 meter cube per day of treated wastewater into the Bald Eagle Creek. The treated wastewater has a BOD5 of 12 mg per liter and a K of 0.12 D1, then D negative 1 at 20 degrees Celsius. Bald Eagle Creek has a flow rate of 0.93 meter cube per second and an ultimate BOD of 5 milligrams per liter. The D of the river is 6.5 milligrams per liter and the D of the wastewater is 1.0 milligrams per liter. The stream temperature is 10 degrees Celsius and the wastewater temperature is 10 degrees Celsius. Compute the DO and the initial ultimate BOD after mixing. So the solution is the DO after mixing is given by the equation I've shown a while ago. To use this equation, we must convert the wastewater to flow to compatible units, that is meter cube per seconds. So what equation I'm talking about is the equation of the QW. And here, QW is equal to 17,360 meter cube per D, and it will be divided to 86,400 seconds per day, and that will be equal to 0.20 meter cube per seconds. For the DO after mixing is then we're gonna use the formula for DO, which is this one, to solve the DO. DO is equal to 0.20 meter cube per seconds times 1 mg per liter plus 0.43 meter cube per seconds times 6.5 milligrams per liter over 0.20 meter cube per seconds plus 0.43 meter cube per seconds, and that's equal to 4.75 milligram per liter. Because the rate constant for the wastewater is given for the reference temperature of 20 degrees Celsius, we must first convert it to the temperature of the mixture of the wastewater and stream water. Because both have temperature of 10 degrees Celsius, the mixture will be at 10 degrees Celsius. So using the equation of the KT, where the theta is equal to 1.135. So K10 is equal to 0.12 to negative 1 times 1.35 raised to 10 minus 20. And that's equal to 0.0338. And now for our LO, so using the formula, LO is equal to BOD5 over 1 minus E raised to negative KT, and that's equal to 77.12 milligrams per liter. Note that we use the subscript of 5-day and BOD5 to determine the value of T in the equation. Now setting LW is equal to LO, we can determine the initial ultimate BOD after mixing using the equation 7.76. So this equation is the equation of LA, which is this one, where LA is equal to the initial ultimate BOD after mixing. In this problem, LA is equal to 0.20 meter cube per second times 77.12 milligrams per liter plus 0.43 meter cube per second times 5 milligrams per liter over 0.20 meter cube per second plus 0.43 meter cube per second. And that's equal to 27.90 or 28 milligrams per liter. Oxygen deficit. The DO-SAG equation has been developed using the oxygen deficit rather than dissolved oxygen concentration to make it easier to solve the integral equation that result from the mathematical description of the mass balance. The oxygen deficit is the amount by which the actual dissolved oxygen concentration is less than the saturation value with respect to the oxygen in the air. So we have an equation of D is equal to DOS minus DO, where D is the oxygen deficit, DOS is the saturation concentration of dissolved oxygen at the temperature of the river after mixing, and DO is the actual concentration of dissolved oxygen. The saturation value of dissolved oxygen is heavily dependent on water temperature. It decreases as the temperature increases. Value of DOs for fresh water are given in Appendix A. The initial deficit, the beginning of the BOD-SAG curve, is at the point where the waste discharge mix with the river. To get the dA, so we have the equation. dA is the initial deficit after river and waste have mixed. dA is equal to DOS minus the quantity of QW times DOW plus QR times DOR over QW plus QR. For example 3 regarding the initial deficit, so we have the problem to calculate the initial deficit of the Bald Eagle Creek after mixed with the wastewater from the town of State College, which can be seen on the example 7.9, but I just put it example 2. Yeah, the stream temperature is 10 degrees Celsius and the wastewater temperature is 10 degrees Celsius as well. So the solution here is with the stream temperature, the saturation value is dissolved oxygen or DOS can be determined from the table in Appendix A. And if you look at it, 10 degree DOS is
11.33 milligrams per liter. Since we calculated the concentration of DO after mixing as 4.75 milligrams in example 2, the initial deficit after mixing is dA is equal to 11.33, which is our DOS, minus our concentration of DO after mixing, which is 4.75 milligrams per liter, and that would be equal to 6.58 milligrams per liter. DO-SAG equation. A mass balance diagram of DO in small reach or stretch of rivers is shown on our figure below. So we have here the legend of RDO in and RDO out is the mass of the DO flowing in and out of reach. W is the mass of DO in wastewater flowing into reach. A is the mass of the DO entering from the atmosphere. P is the mass of the DO entering for algae photosynthetic oxygen production. B is the mass of the DO consumed by benthic demand. M is the DO mass of DO removed by microbial degradation of carbonaceous BOD. N is the mass of the DO removed by microbial degradation of nitrogenous BOD, and R is the mass of the DO consumed by algal respiration. For our mass balance equation, we have an RDO in plus W plus A minus M minus RDO out is equal to 0. As we know, RDO in is the mass of the DO in river flowing into reach. W is the mass of the DO in wastewater flowing into reach. A is the mass of the DO added from atmosphere. M is the mass of the DO removed by microbial degradation of carbonaceous BOD. And RDO out is the mass of the DO in river flowing out of reach. For the Stretter-Phillips DO-SAG equation, D is equal to KD times LA over KR minus KD times the quantity of E raised to negative KDT minus E raised to negative KRT plus dA times E raised to negative KRT, where D is oxygen deficient in river water after excretion of BOD for time t. LA is the initial ultimate BOD after river and wastewater have mixed. KD is equal to the deoxygenation rate constant. KR is the aeration rate constant, and T is the time of travel of wastewater discharge downstream, while dA is the initial deficit after river and wastewater have. In cases where KR and KD is equal, D is equal to KDT times LA plus dA times E raised to negative KDT.
Number 5. The oxygenation rate constant. It is different, or it differs from the BOD rate constant because there are physical and biological differences between river and a BOD bottle. In general, BOD is exerted more rapidly in river because of turbulent mixing, larger number of seeds or organism, and the BOD removal by organism on the stream bed as well as by those suspended in the water. While K rarely has a value greater than 0.7 day 1, negative 1, KD may be as large as 7 day negative 1 for shallow, rapidly flowing streams. However, for deep, slowly moving rivers, the value of KD is very close to that for K. Bosco has developed a method of estimating KD from K using characteristics of the stream. KD is equal to K plus V over H N, where KD is equal to the deoxygenation rate constant at 20 degrees Celsius. V is average speed of stream flow. K is the BOD rate constant determined in the laboratory at 20 degrees Celsius. H is the average depth of stream, and N is the bed activity coefficient. The bed activity coefficient may vary from 0.1 from stagnant or deep water to 0.6 from rapidly flowing streams. So we have here problem. Determine the deoxygenation rate constant for each of the Bald Eagle Creek, which is example 1 and 2, below the wastewater outfall discharge pipe. The average speed of the stream flow in the creek is 0.03 meters per second. And the depth is 5.0 m, and the bed activity coefficient is 0.35. Solution. From the example 2, the value of K is 0.12 to negative 1. Using the equation for Kd, the deoxygenation rate constant at 20 degrees Celsius is Kd is equal to 0.12 to negative 1 plus 0.03 meter per seconds over 5 m times 0.35, and that would be 0.1221 or 0.12 to negative 1. We also note that the deoxygenation rate constant of 0.1221 to negative 1 is at 20 degrees Celsius. In example 3, we noted that the stream temperature was 10 degrees Celsius. Thus, we must correct the estimated Kd using the equation of the Kd. Kd at 10 degrees Celsius is equal to 0.121 to negative 1 times 1.135 raised to 10 minus 20 is equal to 0.034 to negative 1. Reaeration. The value of Kr depends on the degree of turbulent mixing, which is related to the stream velocity, and on the amount of the water surface exposed to the atmosphere compared to the volume of the water in the river. A narrow, deep river will have a much lower Kr than the wide, shallow river. So now we have here the equation to estimate the reaction constant. Kr is equal to 3.9 times V raised to 0.5 over H raised to 1.5. Kr is equal to the reaction rate constant at 20 degrees Celsius. Our V is the average stream velocity, and our H is the average depth. With the speed of the flow in the river and the distance downstream, the travel time may be estimated from the basic relationship between time, distance, and speed. So we have T is equal to distance over speed. To relate time or travel time to the physical distance downstream, one must also know the average stream velocity. Once D has been found at any point downstream, the DO can be found from oxygen deficient equation. Critical point. The lowest point on the DO sag curve, which is called the critical point, is a major interest since it indicates the worst condition in the river. The time to the critical point, or TC, can be found by differentiating Streetel-Fields DO sag equation, setting it equal to 0 and solving for T using the base E value for Kr and Kd. So to get TC is equal to 1 over Kr minus Kd ln Kr over Kd times the quantity of 1 minus dA times Kr minus Kd over Kd times La. So that's for the critical point. And where Kr and Kd is equal, Tc is equal to 1 over Kd times the quantity of 1 minus dA over La. The critical deficit, or the DC, is then found by using the critical time in the Streetel-Phillips DO sag equation. Interpreting result problem. Determine the DO concentration at a point 5 km downstream from the State College discharge into the Bald Eagle Creek. Example 2, 3, and 4. Also determine the critical DO and the distance downstream at which it occurs. So as the solution, the first step is to calculate the KR. KR at 20 degrees Celsius is equal to 3.9 times 0.03 meters per second raised to 0.5 over 5m raised to 1.5. That's equal to 0.0604 day negative 1. Because this is at 20 degrees Celsius, the stream temperature is at 10 degrees Celsius. The equation KT minus K20 theta raised to T minus 20 must be used to correct for the temperature difference. So KR at 10 degrees Celsius is equal to 0.0604 day negative 1 times 1.024 raised to 10 minus 20, and that's equal to 0.04766 day negative 1. The time travel, or T, is computed from the distance downstream and the speed of the stream. T is equal to 5 km times 1000 meters per kilometer over 0.03 meter per second times 86,400 s per d, and that's equals 1.929 d. Although it is not warranted by the significant figures in the computation, we have elected to keep 4 significant figures because of the computation effects of truncating the value. The deficit is estimated using the Streeter-Phillips DO-SAG equation, and that is D is equal to 7.71 milligrams per liter. The dissolved oxygen is DO is equal to 11.33 minus 7.71, and that's equal to 3.62 milligrams per liter. The critical time, or TC, is computed using the equation of TC, and for that we have 1 over 0.04766 minus 0.03442 ln the quantity of 0.04766 over 0.03442 times the quantity of 1 minus 6.58 times 0.0476 minus 0.03442 over 0.03442 times 27.90, and our TC is 17.40 D. And for our critical deficit, or DC is equal to 0.03442 times 27.90 over 0.04766 minus 0.03442 times the quantity of E raised to negative 0.03442 times 17.40 minus E raised to negative 0.04766 times 17.40 plus 6.58 times E raised to negative 0.04766 times 17.40, and our DC is equal to 11.07 milligrams per liter. Solving DO-SAG equation for DO at critical point, or DOC, and using DOC is equal to 11.33 milligrams per liter from table A of appendix A. Given the critical DOC is equal to 11.33 minus 11.07, that's equal to 0.26 milligrams per liter. For the critical DO occurs downstream at a distance of 6.45 D times 86,400 S over D, S per D, 0.03 meters per second times 1 over 1000 meter per kilometer, and that equals 16.7 kilometer. So from the wastewater discharge point. So note that 0.03 meters per second is the speed of the stream. TMDL mass loading. As noted earlier, TMDL calculations are based on the mass loading. To use the DO-SAG equation, as presented here, the mass loading kg over d of ultimate BOD must be converted to a concentration. Following our general approach for calculating concentration from mass flow, we divide the mass flow kg over d by the flow of the water carrying the water. QW, QR, or the sum of QW plus QR. So we have here the mass flow of ultimate BOD over flow of water carrying waste. The mass discharge unit are then converted to mg over d and the water flow rate to L over d so that the days cancel. Convert the discharge of 129.60 kg per day ultimate BOD in 0.0500 cubic meter per second of wastewater flow to a concentration in a unit of milligrams per liter. So I have here a solution. Using the equation we have above, we will be able to get the LW. So 129.60 kilogram per day times 1 times 10 raised to 6 milligrams per kilogram all over 0.0500 cubic meter per second times 86,400 S per D times 1 times 10 raised to 3 L per meter cube, and that would be 30 milligrams per liter.
Number 11, management strategy. The beginning point for water quality management in rivers using the DO-SAG curve is to determine the minimum DO concentration that will protect the aquatic life in the stream. This value is called the DO standard. It is generally set to protect the most sensitive species and that exist or could exist in a particular river. For a known waste discharge and a known set of river characteristics, the DO-SAG equation can be solved to find the DO at the critical point. If this value is higher than the standards, the stream can adequately assimilate the waste. If the DO at the critical point is less than the standard, the additional waste treatment is needed. Usually, the environmental engineer has control over just two parameters, LA or DA. By increasing the efficiency of the existing treatment process or by adding additional treatment steps, the ultimate BOD of the waste discharge can be reduced, thereby reducing LA. Often, a relatively inexpensive method for improving stream quality is to reduce the DA by adding oxygen to the wastewater to bring it close to the saturation prior to discharge. To determine whether a proposed improvement will be adequate, the new values for LA and DA are used to determine whether the DO standard will be violated at the critical point. Under unusual condition, the engineer may artificially aerate the river with mechanical system to increase the DO. When using the DO sag curve to determine the adequacy of the wastewater treatment, it is important to use the river conditions that will cause the lowest DO concentration. Usually, this condition occurs in the late summer when river flows are low and temperatures are high. A frequently used criterion is the 10-year, 7-day low flow, which is a recurrence interval return period of the average low flow for 7-day period. Low river flows reduce the dilution of the waste entering the river, causing higher value for LA and DA. The value of KR is usually reduced by low river flows because of reduced velocities. In addition, higher temperatures increase KD more than KR and also decrease DO saturation, thus making the critical point more severe.
Now we have the nitrogenous BOD. The nitrogenous BOD can be incorporated into the DO sag curve by adding an additional term to Streeter-Phillips DO sag equation. With that, we can arrive with this equation for nitrogenous BOD, where Kn is equal to the nitrogenous dioxygenation coefficient and Ln is the ultimate nitrogenous BOD after waste and river have mixed, and the other terms are previously defined. So that's it for our nitrogenous BOD.
Number 13. Other factors affecting the DO level in rivers. The classical DO sag curve assumes that there are only one point source discharge of waste into the river. In reality, this is rarely the case. Multiple point sources can be handled by dividing the river up into reaches with a point source at the head of each reach. A reach is the length of the river specified by the engineer on the basis of its homogeneity, that is, channel shape, bottom composition, slope, and so forth. In small rivers, rapids play a major role in maintaining the high DO levels. Can be natural deposits of leaves and dead aquatic plants, or can be sludge deposits from wastewater receiving little to no treatment. Some rivers contain large deposits of organic matter in the sediments. Aquatic plants can also have substantial effect on the DO level. As a general rule, large growth of aquatic plants are detrimental to the maintenance of the consistently high DO level. Now we'll talk about the effect of nutrients on water quality in rivers. Causing excessive plant growth are nutrients such as carbon, nitrogen, phosphorus, and a variety of trace elements. So the advantage of this is that it supports the animal community, while the negative effect of this, or the disadvantage, is the thick slime layer on rocks and the dense growth of aquatic weeds. Effects of nitrogen. There are three reasons why nitrogen is neutral to receiving body. So the first one is in high concentration, the NH3 minus N is toxic to fishes. NH3 in low concentration and NO3 negative serves as the nutrients for excessive growth of algae. The conversion of NH4 positive to NO3 negative consume large quantities of dissolved oxygen. Effect of phosphorus. It serves as vital nutrients for the growth of algae. Excessive production of algae can be the result. When the algae dies, they become an oxygen-demanding organic material as bacteria seek to degrade them. Overtax the DO supply of the water body and as a consequence causes the fish to die. Now let's go on with the management strategy. The strategy for managing water quality problem associated with excessive nutrients is based on the sources of each nutrient. Except under rare circumstances, there is plenty of carbon available for plant growth, available from the bicarbonate alkalinity of water and from the bacterial decomposition of organic matter. Major source of trace elements is the natural weathering of the rock minerals. Air pollution control can be a help to reduce the supply of trace elements. The practical control of nutrient-caused water quality problem in streams is based on the removal of nitrogen and phosphorus from wastewater because they are discharged, and using best management practices, or the BMPS, to minimize the nutrients and agricultural runoff.